Well, good morning. Name's Joel Kirshman, and I'm going to demonstrate a new feature of our tool. And we're going to be discussing our product called RFP, our RF Frequency Planning Tool, which we announced a couple of months ago. It's a new feature to our system tool, Visual System Simulator. And in essence, RFP is a tool for designers that are coming up with a novel or a new architect or a radio frequency architect. And it'll give you the capability of doing a first cut analysis of your link, as well as identifying how spurs are generated in the radio link. And through using these slides, hopefully I'll cover everything that can be done in RFP. So what does RFP support? Well, it supports the concept of using a defined RF frequency band of interest. It also supports introducing multiple bands and multiple threats. Through the course of this presentation, I'll define what a threat is and what a RF band of interest is. It supports multiple conversions. We have behavioral models such as Butterworth and Chebyshev filters where you can define a bandwidth and a center frequency. We can also read in touch tone data of a filter. And we do support vendor models. If you install a specific vendor model like a Hittite mixer or a Hittite amplifier, if you install that with the RFP planning tool, that vendor model becomes available to you. So we have behavioral models, vendor models, and data files that can represent components in the link. And VSS is seamlessly integrated with our visual system simulation tool. That means you'll go from the RFP simulation engine, press one button, and we'll drop that RF link into the AWR system tool visual system simulator. And from there on, you can simulate mismatch between components. You can take that same RF link that you developed and start passing modulated signals through that and make such measurements as EVM, error vector magnitude, ACPR, carrier to noise interference measurements, etc. So where do you begin when you're working with RFP? We have the first analysis here is a cascaded analysis, a linear analysis of the link. The measurements can include cascaded noise figure of the link, the IP3 or the gain or the power at each node can be illustrated here in this planning diagram. So each node represents a component in your system, and then they're color coordinated measurements. So these are strictly, once again, linear measurements, or Friss equations are used to calculate these numbers. Earlier I said you can drop the system, this RF architect, into VSS, Visual System Simulator, and start counting for mismatch between components and noise at image frequency. This is your first cut at budget analysis using the tool. Where do you begin? How do you start working with the RFP tool or a radio frequency planning tool? You defined an RF band of interest. So in this here, we're illustrating a band from 960 to 1010 megahertz. That's my band of interest. I can define a nominal power level, a minimum power level, and I can indicate this band as being the active band. This is the band of interest. I expect to see an RF frequency coming anywhere from 960 to 1010 megahertz. That's my defined band. Then I will come here and I'll start selecting components. Earlier I said we can access vendor components. If I install the vendor library along with RFP, I'll come to the palette of components, amplifiers, attenuators, mixers, and filters, go to the manufacturer folder. Here I'm hitting Hittite, and then I can pull in a data file, for example, of an amplifier. In this case, the amplifier is realized by using the P1 dB, the IP3, and the gain. And in fact, it's going to be simulated mathematically based on those numbers that came off the manufacturer data sheet. We have other ways of representing amplifier designs in VSS. You can give us AM to AM curves or AM to PM curves, or you can give us a whole table of intermodulation products and the harmonics that you tested at. So various ways of going beyond a manufacturer's data sheet parameters to do an amplifier in a simulation environment. So the next step is that you'll define your LO frequencies, whether the conversion is a RF minus LO, RF plus LO, or LO minus RF. And you can keep the LO frequency sweep, you can keep the LO frequency fixed, and or you can keep an IF frequency fixed. And ultimately, when you're in this type of environment, you can further analyze that particular mixer model that you're working with. And what does that mean? Is that you can have a spur chart here presented to you in the tool where the x-axis here is the RF. We're going from 960 to 1010 megahertz. I have my LO frequency set at 650 megahertz, so my IF on the y-axis is going from 310 to 360 megahertz. I can click on one of these color-coordinated lines, and it'll tell me how low that intermodulation product is relative to the carrier. So in this instance, I select this yellow line, which is hard to see from out there, and it'll say it's 64 dBc down from carrier. So that's a Spur table that you can populate with your own numbers or read directly from a data sheet. Or if you like, you can also run the mixer using a mathematical formula of representing a double balance quadrature mixer and using Bert Henderson's model. So either Spur tables up to 10 by 10 or a mathematical model can represent your mixer. In addition to looking at it in this format, you can have a whole table here of the N by N products and their following frequencies and their power levels. Then you build up your link. You'll go and access a bandpass filter, a conversion, another filter, an amplifier, a filter, a second conversion, and then lastly a filter. So we can have multiple conversions in this link. We can have multiple systems in this tool. And one way of looking at your link is here. You can look at the resulting spurs generated in a tabular format, the IM products and their corresponding power levels. So there are different ways of analyzing this RF link. That's the first go. The second go of analyzing a link is that you can look at a CW signal passing through and all the intermodulation products being generated in a tabular format or in a visual format. So our RF frequency here is 960 megahertz. Our IF is 110 megahertz. The resulting spurs and their product power levels are displayed. And over here you can look at it in a tabular format. You can sweep the RF input frequency. So here I swept my RF to 100 megahertz. My IF went to 150 megahertz. And I can see multiple products being overlaid over here around 97 megahertz. So RF sweeping, LO fixed, not fixed. RF sweeping and the LO is fixed at 650 megahertz. So that's 150 megahertz, I'm sorry. So one way of looking at things, sweep RF, look at the products generated as you have the LO fixed. Or we can indicate to the tool, let's keep the IF at 150 megahertz. The LO of the last conversion will change as I switch the RF. So now I'm going to switch the RF frequency. We'll maintain an IF of 150 megahertz. So I'm at 1,005 megahertz. Sweep it to 985 megahertz. My IF is still at 150 megahertz. The second LO went to 185 megahertz. So that second LO will track the RF, always to maintain 150 megahertz IF. And then we look at the resulting products that are generated. So now we're dealing with our active band. Okay? The next thing we're going to do is introduce a threat or an unwanted band. So we'll go back to defining bands. There's our original band, band 1. That's our active band. Then I indicated to the tool that I have a neighboring band or a threat band or an interfering band. And I said that band is from 940 to 950 megahertz. You can have multiple active bands, you can have multiple threat bands. Here I'm just illustrating one active and one threat. And the threat's from 960 megahertz to 1010 megahertz. I say, okay, well, I've just introduced here a 940 megahertz interfering signal minus 10 dBm. And then I look at the resulting spur generated. So we see an additional 5 products come within band, in the band of interest, the IF band of interest. And we can click on these spurs and a table will appear and will show me the origin. Why did these signals start appearing? What was the origin of one of these frequencies? So here, that's the table format of the spectrum plot that we saw. I see a system 1, band 2. So every time you see band 2, that's the threat band. And then I can look at the origin of this 160 megahertz signal. How is that 160 megahertz signal generated? Well, there's the mathematics. Minus 940 megahertz times 2 of the 650 megahertz. The origin is illustrated there, 160 megahertz. What caused that signal to be generated? And another way of looking at this is that we have this frequency band response. So you can see here the signal of interest is in purple, 1 minus 1, the difference. And you can see as it drops off or increases power within the constrictions of that last bandpass filter, and you can monitor all the products in this format here, what we call a frequency band response, how things are going to vacillate with the intermodulation products in the filter. So when I built the design, I started over here with my very first filter being a fifth order filter, and I had this 160 megahertz signal at minus 65 dBm. Okay, previously I think I had a third order filter. Yeah, a third order filter, the 160 megahertz signal that was generated as a result of having an interfering band was minus 47 dBm. I adjusted the order of the very first filter, and I can see I reduced that 160 megahertz threat to minus 65 dBm, and I got rid of 4 of those intermodulation products that were resulting from the threat band. And there's the caption of what I've just said. And using a fifth order filter, I can reduce that signal to minus 65 dBm and reduce many of the spurs. So maybe that's the solution of this RF architect design. Increase the order to reduce the number of spurs generated in the band of interest. And once you're done, you click the button and then you'll fall into the VSS. So this is the rendition of that link that we saw previously in RFP. Then I said, whoops. Then I said here, generate the visual system simulator system diagram. And this is going to drop me into the AWR tool, the VSS tool, where I can start performing a more in-depth analysis, meaning that I can count for mismatch between components. I can account for the order of the image rejection filter, how that impacts on noise figure. I can take this design, replace that CW signal with a WCMA or LTE signal, and then start making a conformance type of measurement, as I mentioned before, such as ACPR, error vector magnitude, etc. So in conclusion, RFP is one of the essential analysis tools when developing a radio communication system. It's fast and efficient, and you'll have a first go at calculating the noise figure, P1 dB, and signal-to-noise ratio, and ultimately the tool is integrated with the AWR designing environment and VSS. You can start replacing components with microwave office circuits as well in the VSS environment. So you can start all the way at the very highest level of abstraction, your RF architect, all the way down to the actual design of that component at a circuit level. As my colleague before mentioned, Dustin, here's the list of our present micro apps that we're going to be doing throughout the week, where we're located, and as Dustin mentioned, we'd be more than happy to have you guys come to our party tomorrow evening. Any questions from the audience? Yes?
Looking in IQ mixes,
yes.
as well as this, and do you have a reference, or you mentioned Bert Henderson's work, but do you have a reference for that? Or?
Yeah, so the question is, can we put an IQ modulator into the design? And I said, yes, we do have a reference to Bert Henderson's paper when he was at WJ Communications. That'll explain all the mathematics of that model. The alternative is, as I mentioned before, you can also read in a Spur table, an n-by-n matrix, and we'll simulate according to that. Or you can give us a suppression table, 3 columns of information, the index of the LO, the index of the input, and then the suppression value. So different ways of doing an IQ type mixer, quadrature mixer. Any other questions? Well, thanks for your time.